The Gresham College lecture that you're listening to right now is giving you knowledge and insight from one of the world's leading academic experts. Making it takes a lot of time, but because we want to encourage a love of learning, we think it's well worth it. We never make you pay for lectures, although donations are needed. All we ask in return is this: send a link to this lecture to someone you think would benefit, and if you haven't already, click the follow or subscribe button from wherever you're listening right now. Now, let's get back to the lecture.
So thank you very much for coming. We're going to talk about the mathematics behind Sudoku. On the way, we're going to meet a sacred Chinese turtle. We're going to visit a bleak Welsh hillside and a Parisian apartment block. We're going to encounter different kinds of number squares, like Latin squares that we'll meet soon. But let's just begin. Probably everyone in the room knows what a Sudoku is, but just in case, let's establish the ground rules. So a Sudoku grid, this is a completed one. It's a square of side 9, and it features the numbers 1 to 9 with the following rules. These numbers have to appear exactly once in each row, in each column, and in each of these little 3x3 blocks. So that's what a completed Sudoku grid looks like, but that's not what we see when we start the puzzle. We see a partially completed grid, something like this, and then our job is to use just the rules that we know to fill in the rest of the numbers. You may not have noticed this, but by convention, the squares that are filled are usually symmetrical. They have a rotational symmetry. So if you do a 180-degree rotation, the numbers aren't going to match, but the squares that are filled have that pattern. And if we are trying to create a Sudoku puzzle, it must be the case that this grid can be completed in exactly one way, so there's a unique solution. There is a solution, and that's got to be unique, only one solution, and it should be obtainable without guesswork in an ideal world. In an ideal world. So it should be obtainable. Occasionally, one or two of us may resort to guesses on occasion. But let's pretend we never do that. So this is not, by the way, a masterclass on how to solve a Sudoku, because there's lots of resources about that you can find. There are books, there are websites. But just to sort of give a basic idea of the sort of thing you might do, we filled in a few entries already. So at this point, of course, you are going to use these rules constantly. So, for example, you could say that, look, in this row, there's only one number that we haven't got, and there's only one space. So we've got to put a 1 in that space. There it goes. Now we've got a column that only has one number missing. The numbers 1 to 9 must appear exactly once in each row, in each column, in each block. So in this one, we can see that there's, a 3 missing, and we can put that in. And then now, look, in this central block, we've now arranged things so that there's only one gap there as well. And we can put a 6 in that gap. So we can proceed like this. We can get slightly more sophisticated. So there's one technique which is very useful, which is often called slicing. So imagine cutting your Sudoku into 3 thick slices, each of which contains 3 rows, and it also contains 3 blocks. So you can see I've highlighted the middle slice of my Sudoku cake there. Now that's useful to notice because it means in that slice, every number is going to show up exactly 3 times. Once in each row, once in each block, but 3 times in total. So if we look at, say, the 6s here, there are 2 6s so far in that block. We can eliminate lots of possibilities for where the remaining 6, there must be another 6, where it could go. So it can't go in either of the rows that contain a 6, so it's not in that row, it's not in that row. It can't go in either of the blocks that already contain a 6. So it's not in the left-hand block, it's not in the middle block. And we can see there's only one place it can go, because it must go in the top row of the right-hand block, and there's only one empty space in that row. So that's great, so we can pop our final 6 in there. And of course, well, it's slightly unconventional with cake, but you can slice vertically as well, and do the same thing with vertical slices of your Sudoku. Another option available, which is useful sometimes, is even if you can't absolutely pinpoint where numbers go, sometimes you can narrow it down, and you can get pairs of numbers that have to go in some order into 2 spaces. So, for instance, if you look at this vertical slice here, look at the 9s. We've got 2 9s. Where's the third one going to go? It's got to go in the right-hand column, because the other 2 columns have a 9, and the top block. So there's 2 vacant cells where it could possibly go. There's 9. We don't know which one it goes in. But there's also 3s, and by exactly the same reasoning, the other 3 that is in that vertical slice must go in one of those 2 squares that are highlighted. Now, we don't know which way around they go, but we know that those 2 squares contain a 3 and a 9 in some order. So no other squares in that little block can contain a 3 or a 9. So even though we don't know which is which at this point, that can help us with other entries. For instance, in this row up here, there's got to be a 3 somewhere. We haven't got one yet. But it can't be in either of those little empty spaces on the right-hand end of that row, because we know that the 3 that must be in that block is in the top or the bottom square that we've highlighted. It doesn't matter which one it is for us to deduce that it's not in that middle row there. So we know that the 3 has to go on the left-hand end of this row where I've put it. So these kind of ideas, and some others, can help you to complete the Sudoku grid. And at each stage, you are proceeding using just, pure logic. You're not guessing at any point. As I've said, lots of resources you can find if you want to learn lots more tips and tricks about Sudoku. If you want to be loyal to Gresham College, you can seek out the book on Sudoku by our former Gresham Professor of Geometry, Robin Wilson. But that's my recommendation anyway. But mathematically speaking, what have we done? We haven't actually had to do any arithmetic with the numbers. So if people say correctly that Sudoku is mathematical, sometimes there's a misapprehension that it's mathematical because it's got numbers in it. But that isn't the reason it's mathematical. The reason it's mathematical is because we're using the structure and we're thinking logically about how to complete the puzzle. And there are also mathematical questions we can ask about Sudoku. For example, how many possible complete Sudoku grids are there? Can we count them? Can we work out, classify them? How many puzzles are there? That's slightly different, because a puzzle is a partially completed grid which has a unique solution that can be arrived at without guesswork. So how many of those, and can we make those? And related, how many clues do we actually need to be able to do this? So if you just put one number into an empty grid, of course you're not going to be able to find a unique solution to that. What's the minimum number you need in order to be able to actually finish that puzzle? It might be very hard, but what's the smallest number you need? But let's begin by saying Sudoku is, in the UK at least, fairly recent in geological timescales. So the first Sudoku ever in the UK, printed in a national newspaper, was in November 2004 in the Times newspaper. So it's fairly recent coming to the UK. But, we sort of all feel that, Sudoku is this ancient Japanese thing that, imagine the Sudoku master crafting this perfect puzzle on the slopes of Mount Fuji or something like this. That is complete nonsense. It sounds like this picture I've just made that's just as a massive lie. Sudoku was invented in America in the 1970s. It wasn't called Sudoku then, it was called something like Number Place, and there were these puzzles that were like Sudoku, and then they got picked up by a Japanese puzzle magazine who started printing them about a few years later, and they really took off in Japan, and then they made their way to the UK and indeed back to America. But these puzzles, this kind of number grid, is less than 50 years old. And in the grand scale of mathematical ideas, that's very recent. There are much older squares of numbers, and we're going to go now on a little journey through the history of some of these squares of numbers, partly because they'll feed into our thinking about Sudoku, but partly because they're just super interesting already in their own right. And we're going to begin with the oldest kind of number square, and that's the magic square. So this is a picture of what's believed to have been the oldest magic square that we know of, and it's called the Loshu square. So this is a picture from a Tibetan scroll. This is some centuries after the square probably originated. Let's put the numbers into modern format. Here they are. And this shows you this is a magic square. So what's a magic square? This time we do need to do some arithmetic with the numbers, because a magic square is one where the sum of the numbers in every row, every column, and every diagonal is the same. We call it the magic number. So if you pick a row or a column or diagonal of this, and everyone picks one, and you should find that the sum of the numbers is 15, always. So this is a magic square. This square is reputed to have originated in the following way. There was a big flood in China, and the people were trying to appease the river god by making sacrifices to say, please stop the flooding. And as a sign that their prayers were going to be answered, the god sent a sacred turtle, and he crawled out of the river, and on his back, into his shell, was carved this magic square. Okay, so that's the origin, it is claimed, of this magic square. It's a particular kind of magic square. It features the numbers 1 to 9. So that, you can have other ones which don't do that. If you start with the first, however many numbers that you need, in this case, if it's an order 3 square, so it's 3 by 3 square, then you need to fill it, you need the numbers 1 up to 9. That's called a classical magic square, okay? But they don't all have to be classical. So the oldest order 4 magic square that we know about is this one. This is not a classical magic square because that would have to contain the numbers 1 to 16. This doesn't, but it's still a magic square. The sum of the numbers in each row, column, diagonal is constant. And so this comes from a book, an old Indian book by Varahamihira, and its purpose, stated in the book, was to give you different recipes for making perfume with 4 ingredients. So here's what you do. You get your 4 ingredients, A, B, C, and D, and you pick a row, column, or diagonal. Let's say we pick the first row, and that tells you to use 2 quantities of ingredient A, 3 of ingredient B, 5 of C, 8 of D. And the total amount, because it's a magic square, whichever row, column, or diagonal you pick, the total volume of the perfume that produce will be the same. So this is what was stated the purpose of this square. So that's an order 4 magic square. Now, Sudoku grids, let's have a mini Sudoku. You can see what it is. It's got the numbers 1 to 4 instead of the numbers 1 to 9, but the same principles apply. Those are not magic squares necessarily, because the sums along the diagonals do not have to fit in with this rule. They're called semi-magic squares, an example of a semi-magic square. And so a semi-magic square has the same sum of the rows and the columns, but we don't mind about the diagonals. Now, Sudoku sort of gets into that classification. It's not cheating exactly, but of course, because this one has the numbers 1, 2, 3, and 4 in every row and in every column, obviously the sum of those numbers is always going to be the same. They're the same numbers. So Sudoku is a semi-magic square, so-called. Now, the most famous magic square in Western art is in this picture, Melancholia by Albrecht Dürer. You might not be able to see it so clearly because it's in the top right-hand end of that picture, but I've enlarged it so you can see it better. So this is a classical, it's got the numbers 1 to 16, order 4 magic square. The picture was made in the year 1514, and you can see 1514 is those 2 numbers in the middle of the bottom row. 1514 was the year that Dürer's mother died, hence the Melancholia. But there's lots of other symbolism in this picture. For example, at that time, different planets were associated to different characteristics of various kinds. The planet Saturn was associated with melancholy. It was also associated, completely independently, I should say, with geometry. Geometry does not make you sad, makes you happy. But that's why there's a lot of geometry going on in this picture as well. Now, magic squares of different sizes were also associated to different planets. But the size of magic square that's associated to Saturn is, if I remember rightly, order 6, 6 by 6 square. So what's this 4 by 4 square doing in there? Well, if you're feeling melancholy, an antidote to that might be to do something a bit more jovial. And jovial things are associated with the planet Jupiter, because Jove is another word for Jupiter. So 4 by 4 magic squares are associated with Jupiter, but this is an antidote to your melancholy. So that's what that square is doing in there. Now, we could work out the magic number of this particular order 4 classical magic square. We can just add up the numbers in one of the rows, columns, or diagonals. But we don't have to, because it turns out that every classical magic square of a given order has the same magic number. Here's that Dürer one again reproduced here just for a note. We can prove this, and we do something that mathematicians quite like to do, which is to work out the same thing in 2 different ways, and then say, these things, they're both equal to this middle thing, so they're the same as each other. And the thing we're going to work out, is the sum of all the numbers in that square. You'll see why this helps us. So if you want to work out the sum of all the numbers in that square, well, we just have to add up the numbers 1 to 16. Fine. Now, there's a cute little trick to doing this without actually having to do any work. It's another thing mathematicians like. So we can also write that S, that sum, we can just add them up in the other direction, right? 16 down to 1. And the reason that's useful is, if we now add those two equations together, on the left, we've got twice the sum, the thing we're interested in. On the right, you can see all those pairs add up to the same thing, 17. 1 plus 16, 2 plus 15, all the way down. So on the right, we've got 16 lots of 17. On the left, we've got twice the thing we're interested in. So if we just halve everything, we now find that our sum S is half of 16 times 17. We don't need to work that out yet, or indeed ever, because there's another way to work out the sum of all the numbers in the square. And that is to notice every row sums to the same thing, the magic number that we're trying to find. Let's call that magic number M. Then we know that this sum of all the numbers in the square is just 4 lots of the magic number, because we've got 4 rows. Great, so now we've got 2 different expressions for our S, make them equal to each other, and we can find out M. We don't even need to find S, not interested in that, we can find M directly. It's 1/8 of 16 times 17. And we're at the point now where even I can do that with a live audience. 1/8 of 16 is 2, and 2 times 17 is 34. So the magic number, and you can check this for the Juris square, but it will be true for any order 4 classical magic square, the magic number is 34. Has to be. And really, the fact of it being 4, was not involved in any of this stuff. We didn't need it to be 4, that wasn't special. And you can actually use this same process to work out the magic number of any order n is of course our favorite number, any classical magic square of order n, so an n by n square. It will contain the numbers 1 up to n squared. So if you just replace all the 4s in what I did before with n's, the same reasoning applies, and you get this formula for the magic square, the magic number of a classical magic square of order n. So we can work out, for example, when n equals 3, what's that, the low shoe square, the magic turtle square? If n is 3, you can put in that into this equation, and you find that the magic number is 15. And here is the square, and you can check, yes, indeed, that's true. It also shows you that there cannot be a classical magic square of order 2. And the reason for that is if you put n equals 2 into that little formula there, 2 squared plus 1 is 5, and half times 2 is 1, so you get 5. That would be the magic number. But if you try and actually make 5, what's got to go with 1 to make 5? This square would have to have the numbers 1, 2, 3, and 4 in it. But 1 would always have to be paired with 4. So 4 would have to go actually in every single one of those gaps to make this be a magic square, and that's not allowed. Where are 2 and 3 going to go? So there are no classical magic squares of order 2. But it turns out there are definitely classical magic squares of every other order. So 2 doesn't work, everything else you can do. And methods for finding these things were being developed from hundreds of years ago. One of the most interesting writers and mathematicians working on magic squares was Muhammad ibn Muhammad al-Falani al-Kishnawi, who was born in, I put this sort of red blob there, he was born in what's now northern Nigeria, and then he moved north and he lived and worked mostly in Cairo in Egypt, and it was there when in 1732 he wrote a treatise on magic squares. And in that he did loads of stuff. He found all the order 3 classical magic squares, and he gave a way of producing a magic square of any odd order, so order 5, order 7, and so on. And there are algorithms that produce all other sizes as well. I'm going to show you his method. You might want to try it for making a 7 by 7 magic square on your way home on the train or something. So here, let's make a 5 by 5 one. And it's the same rule for any size, as long as it's an odd number. So you put a 1 in the middle of the top row, and then the basic principle is you move upwards and diagonally to the right. So up 1 square and right 1 square. Now already you're thinking, but Sarah, you can't move up 1 square. You're already at the top. So what you do then, you imagine you're playing like an old-fashioned game of Space Invaders. This may be you guys in the olden days. there were these games where the memory on the computer wasn't very high. So when you went off the top of the screen, you just reappeared at the bottom of the screen, kind of saves memory in producing the game. When you go off the right-hand side of the screen, you reappear on the left-hand side. So that's exactly what you do with this method. So with this one, if we go up one, that brings us, actually, we reappear at the bottom of the square. And then you go one to the right, so you're moving diagonally. So your 2 goes there, and then you move diagonally, up 1, right 1, 3, up 1, right 1, well, we loop back to the left-hand side, 4, move diagonally again. Now, 6, we want to put where that 1 already is. The rule in that situation is you just move down a square instead. So we get 6 here, then we're moving diagonally again, 7, 8, 9, 10. Oh, our way is blocked, move down, then diagonally from 11, 12, 13, 14, 15. Our way will be blocked again. We want to put 16 where the 11 is. No worries, we just move down a square, 16, and then we can finish 17, 18, 19, 20. Oh, we're blocked, move down, diagonally, 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 and there we are. So that, I mean, you can check, I'm not going to do all the additions right now, that indeed is a classical magic square of order 5. So that's the method, and that will allow you to create one of any odd order. Okay, so the great thing is, once you've got one magic square of a given size, you can make more. This is, again, mathematicians really like making use of something we already have and using it many times. So here is our Loshu square, sacred turtle sitting on the top. With that square, we can make another one. And what we do is we can rotate that square 90 degrees to the right. And what you get is another magic square. The reason is that the rows have become columns, the columns have become rows, the diagonals are still diagonals, but it doesn't affect the sums. So you still have this same magic property. So that's one of the symmetries of a square. Actually, any of the symmetries of a square will still give you a magic square. You're not affecting that property. There are 8 symmetries of a square, including the one where you just sit there and don't do anything. There are 3 kind of rotations you can do apart from that, and then there are reflections in the various symmetry lines. So from one starting square, that actually gives you a set of 8 magic squares. So 8 for the price of 1 is a pretty good deal. Those 8 squares, we call those the orbit of the original square. Because the orbit is everywhere you can get to, and we're getting there by symmetries, which are, of course, wonderful. So our original Loshu square could give us 8 squares. We can also use this idea to find actually all of the order 3 classical magic squares. So these 3 by 3 ones. Here's what we do. We say, start with a blank square. Where's 1 going to go? Where can we put 1? Well, to the options. Now, remember, the magic number here is 15. So the sum of every row, column, and diagonal is 15. So wherever the number 1 goes, in its row, in its column, and if it's on a diagonal, you've got to have 2 other numbers, and the sum of the 3 of them is 15. So the sum of the 2 mystery numbers is 14. And there's actually only 2 ways to do that. You can have 9 plus 5, or 8 plus 6. You can't have 7 plus 7, you've only got 7. So there's 2 possibilities for 1, to be able to go with 1 to make a row, column, or diagonal. So 1 cannot go in the center, because then it's involved in 4 sums, a row, a column, and 2 diagonals. It can't go at a corner, because then it's involved in 3 sums, a row, a column, and a diagonal. So it must be in one of these off-diagonal places. That's the only option. We don't know which one, but what we're going to do is we're going to say, well, I'll just rotate it until it's on the left, and I haven't lost anything, because when I'm done with this and I've got all the possibilities, I can then reproduce all the ones I rotated by just working out, these orbits. So we can assume without any worrying that 1 is on the left-hand side there. Now, where is 9? 9 has the same problem as 1. It only can fit with 2 different pairs of numbers to make 15. Here they are. It can go with 1 and 5, or it can go with 2 and 4. That's the only possibilities. So again, 9 cannot go in any square where there's a diagonal. It can't go in any of these 3 places, because then it would be involved in at least 3 sums. We know that 9 must go with 1 in either its row or its column, so there's only one place left. It must be like this, and then 5 must be in the middle. And the column containing 1 must have a 6 and an 8 in it, in some order. But again, we don't really care which way it is in the particular square we're thinking of, because we can just reflect it and then assume that 6 is at the top. And we'll do the orbit and get everything back when we're done. Now, this is great because at this point, we now know we have got actually everything that allows us to complete the square. Because the 2 diagonals have 2 of the 3 numbers, that means there's only one option for the remaining ones, and then we can fill in those last 2 squares. We've got our square. So what we've shown is that every single order 3 classical magic square is in the orbit of this guy. So we can just reconstruct all of them. There they all are. Are those the ones you can get by rotations? These are the ones you can get by reflections. That is it. That's the full list. So the low shoe square must be somewhere in there. I don't know if you spotted it. Here it is. That's it. There are 8. Now, you could say there are 1. There's 1. But it's just 1 and then all its symmetries. So if you want to say that, and that's often what mathematicians will do, if we're trying to work out how many of these magic squares there are of different sizes, by that same token, so if we're saying somehow there's really just 1 of order 3, then here are the numbers which grow absolutely vast of how many there are of bigger, bigger orders. And that order 6, which is a ridiculously large number, it's got a little question mark over it because it's still not absolutely confirmed. Even though magic squares have been studied for thousands of years, it's still not absolutely confirmed that this is the exact number. There's lots of computer checking that's being done. This is the latest as at September this year. They're pretty sure, but they're not absolutely certain. So vast numbers. And we have, if you think about order 9, which is kind of comparing to Sudoku, we don't even know at all how many there are of that size. That's how huge this search space is. But this is for classical ones that involve the numbers 1 up to n squared. If you're allowed to put any numbers you like in, there are infinitely many. And the reason is, once you've got 1, is that perfume 1 from before, what you could do is double all the numbers in that square, that'll still be a magic square. Or treble, or multiply by anything, and you'll still get another magic square. If you multiply all of the entries by the same fixed constant, the answer will still be a magic square. And if you've got several different magic squares, you can add them together and make more. So once you've got 1, you can get infinitely many. So that gives you, if you remove the classical requirement, you can get infinitely many magic squares. And we're going to move on from magic squares, but just to say, there's other kinds of ways you can explore. You can think about magic cubes. You can think about different magic. So this one in the middle, it's not a magic square by our definition, but in this square, the product of the numbers in every row, column, and diagonal is constant. So that's a different kind of magic. And then on the right, this is cool, this is an anti-magic square. The requirement here is that the sums of the rows, columns, and diagonals must all be different. So there's lots of scope for exploring, which is cool. Okay, let's think about another kind of number square, Latin squares. So Latin squares, which are in the title of the lecture, they are, Sudokus are Latin squares, but not necessarily vice versa. Because a Latin square requires you, this is an order 9 one, it's a Sudoku as well, as it happens, but the numbers, in this case, 1 to 9, appear exactly once in each row and in each column. Sudoku have an extra requirement. They also need the numbers to appear once in each block. So every Sudoku is a Latin square, but not every Latin square is a Sudoku. Now, Latin squares have loads of interesting applications. One of them is in experiment design. So here is a Latin square on a hillside in Wales. What they were doing here was they were trying to look at different species of tree and see how they did in harsh weather conditions. Now, when you're doing that, you want to kind of get rid of any extraneous things that might make one tree do better than the other, but for kind of not the thing you're looking for. You need a very big patch of land to do an experiment involving 5 species of tree. So you can't guarantee, it's impossible to guarantee, that the soil conditions, the humidity, the moisture content, the aspect of the slope, all of those things, you can't make them completely constant across an area of land that big. So instead of having plot 1, plot 2, plot 3, and plot 4 and plot 5, what you do is to create a Latin square, a 5 by 5 array, and you have a plot an area of land for each species, 1 in each row and in each column. And that kind of, separates them out and hopefully then has a sort of sample of each part of the different bits of land. so that it's a fairer experiment somehow. It gives you more robust data. Now, we talked about order 3 Latin squares. You can think about order 3 magic squares. We can think about order 3 Latin squares. Here is one. So this would have, if it's numbers, you'd want the numbers 1 to 3 in each row and in each column exactly once. But it doesn't have to be numbers, as we've seen. It could be trees or it could be colours. How many possible ways are there? Well, if you've got your first row, and I haven't specified how I'm assigning these colours to the numbers, but here's your first row. You can then think about the first column. There's only 2 ways to finish that. Here they are. And actually, it turns out, once you've got this far, the rest is determined. Like, there's only one Latin square that looks like each of these kinds. Here they are. So now there's 2 kind of basic Latin squares, but we need to know where to put the numbers. So which number is going to be red? Well, there's 3 possibilities, 1, 2, or 3. Once you've chosen that, there's 2 possibilities for what's going to be yellow, and then whatever's left must be green. So 3 times 2, 6 possibilities, meaning there are 12 order 3 Latin squares. And the numbers go up, but it's not as crazy as for magic squares. Here's some numbers. They're big numbers. Order 6, a mere 821 million. And we do know exactly how many there are of order 9. It's that rather large number here, 10 to the power 27. 5 times that. So we know how many there are of order 9. It's a smaller problem. Not much smaller, but it is a bit smaller. Now, why are they called Latin squares? To answer that, we need to see an old puzzle. This is quite a cool puzzle. You take a standard pack of playing cards, and what you do is you take the top 4 value cards from each of the 4 suits. So the Jack, Queen, King, and Ace, from each of the suits, which are spades, hearts, clubs, and diamonds. That gives you 16 cards, and your job is to arrange them in a square so that in every row and in every column, there is exactly 1 heart, 1 spade, 1 club, 1 diamond, so 1 of each suit, and exactly 1 of each card value. So there should be 1 king, for example, in each row and in each column, and there should be 1 diamond in each row and each column. And implicit in this, of course, is, you've got a standard pack of cards. You should have each pair occurring exactly once. So like 1 king of hearts, 1 ace of spades in there. Now, this has lots of solutions. It's a fun puzzle, but after a while, maybe you could do it. A little bit after this, in the 19th century, in the court of Catherine the Great of Russia in Petersburg, they were all trying to solve the 36 officers problem. That is exactly this card problem, but bigger. In this problem, you have 6 army regiments and 6 ranks in each regiment. So you have 36 soldiers in total, and you have to arrange them in a 6x6 square such that in every row and in every column, there is 1 of each regiment and 1 of each rank. And no pair is repeated, so you don't have like 2 generals from regiment 1 or something. So what we've got here, actually, let's take with the cards, you've got 2 Latin squares happening at the same time. You've got a Latin square with the suits, one of each suit in each row and each column, and you've got a Latin square with the card values, 1 in each row, 1 in each column. So you've got 2 Latin squares overlaid with this extra requirement that every pair of objects occurs exactly once, 1 ace of spades. So this kind of pairings where you have 2 Latin squares together that have this special relationship with each other, we now call those orthogonal Latin squares. But when Catherine the Great couldn't do this problem, and she asked a nearby mathematician to help her, the guy she asked, who was visiting St. Petersburg at the time, was one of the best mathematicians of all time, Leonhard Euler. And when he started thinking about this problem, he realized that what you had was 2 of these particular squares, and he used some notation. In the first square, he called the things in that square, the set that was being used, he labeled them with Latin letters, A, B, C, D. And in the other squares, he labeled the things in that set with Greek letters, alpha, beta, gamma, delta, and so on. So he called them Greco-Latin squares. We now call them orthogonal Latin squares, and Latin squares is kind of a back formation from that. Because if you're just dealing with one of them, we just call that a Latin square now. But that's where that came from. And he asked himself, well, actually, can we always make these things? We know we can do it with the cards. That's order 4. He could not do it either for the 36 officers. He couldn't solve that problem, the n equals 6 version. He realized he could do, whenever it's an odd number, he could do it. Whenever it's a multiple of 4, he could do it. It's impossible for n equals 2, just like magic squares. He couldn't do it for n equals 6. So his conjecture is that you can always make these things, these orthogonal Latin squares, unless your n, the size of the square, is even but not a multiple of 4. So it's 2 more than a multiple of 4. So you can't do it for n equals 2. And he conjectured you can't do it for n equals 6 or 10 or 14 or any of these, but you can do it for everything else. Now, Euler, as I said, one of the greatest mathematicians of all time, and so when he conjectures something, you tend to believe it. So it was a great shock when in 1959, 3 mathematicians found order 10 orthogonal Latin squares. It was on the front cover of Scientific American, it was all like world news, exciting. And so this was kind of relatively recent mathematics when, I'm sure you can already tell where this is going, this is the ideal way to structure your novel. Yes? So, in 1978, Georges Perec structured his novel Life, a User's Manual around these order 10 orthogonal Latin squares. He set it in a Parisian apartment block, 10 by 10, 100 rooms, and every chapter happened in a different room. And he gave the chapters a unique flavour. And what he did was he'd have particular characteristics or objects, and he put them in lists of 10. So it might be like fabrics and colours. And he used the orthogonal Latin square structure to ensure that each pair from these sets occurred in exactly one chapter. So there's only one chapter, that would have red silk in it. There's only one chapter that would have green velvet, something like this. So every chapter gets its unique flavour from this structure. Now, the book actually, one of the main themes of the book is failure. Lots of the characters are trying to complete things, do things. One of them is trying to complete a lot of jigsaw puzzles of particular places, and he isn't able to do it. And so then what better structure to put under your book than this emblem of the only time almost that Euler, this great mathematician, actually failed to predict something. So this is, it fits in with the book. There's another really cool bit of structure. How do you decide which room you're going to have in your next chapter? Well, the stories follow a knight's tour of a 10 by 10 chessboard. But remember, this is a book about failure. It only has 99 chapters. The tour is never completed. And I love what he blames one of his own characters. He says the little girl on pages 295 and 394 is solely responsible for this lapse. So it's very cool. Now, obviously, this is the most important application of Latin squares. But occasionally there are some, the real world is overrated, but there are some other applications. I just want to mention one, and then we're going to go back to Sudoku. So the one I want to mention involves a kind of extension of this idea of these orthogonal Latin squares, 2 Latin squares that you put them on top of each other. They're both Latin squares, and every pair that you see from the sets that are involved occurs exactly once. One ace of spades rule. It turns out that if you're lucky, sometimes you can make more of these orthogonal squares. In other words, you can have a whole set of Latin squares of a particular size where every pair of them has this property. They are orthogonal. And so you call a set like this a set of mutually orthogonal Latin squares, which is a long phrase. Now, can we find these things? We know, sometimes you can't even find 2 orthogonal Latin squares. In the case of the officer's problem, you couldn't do it, it's impossible. But sometimes you're lucky. And you're lucky when the order of the square, so the size of the square, let's call it Q, when that number Q is either a prime number or a power of a prime number. Then you can guarantee that you'll be able to find a set of Q minus 1 mutually orthogonal Latin squares. So when Q equals 3, for example, that's a prime number, we can guarantee that you can find 2 orthogonal Latin squares. So that's one of the ones that actually Euler managed to find. Now, what use is that? Well, it turns out there is an application in a rather unexpected place. It's when you want to send messages, they don't have to be secret, but they're sent across what we call a noisy channel, where, for example, maybe you're like a space probe 150 million miles from Earth, and you're sending a signal back, and, that going across all that distance of space, every so often, like a passing neutrino will bump into you and maybe turn one of your 1s into a 0 or something like this. So it's that kind of situation where sometimes a message can be corrupted a little bit, and you want to still be able to understand it at the other end. So what you don't want to do is just send, say you're wanting to send yes or no, and maybe yes is 1 and no is 0. If you just send that yes or no, if that's a small chance, but if that message gets corrupted and it's only one letter that you're sending, when you receive on the other end a message, you can't tell that something's gone wrong. You're expecting a 1 or a 0. If you receive a 0, who knows whether that was what was meant. So what you can do is you can add a bit of redundancy to this, a sort of a checking mechanism. So for instance, suppose you want to send yes or no. What you do is to duplicate your message. So now you can either send 1, 1 for yes or 0, 0 for no. And we can assume that it's quite rare for there to be any kind of problem, not very many errors are introduced. We can assume, let's say, that at worst, there'll be one digit that gets tweaked. So us on the receiving end, if we receive 0, 1, we know that is not a message that could have been sent. We've got a collection of messages that could be sent. We call that the code. The code words here would be 1, 1 and 0, 0. We receive 0, 1, something's gone wrong. So we have detected the error, but we don't know what was originally said. However, if we send everything 3 times, which is a bit inefficient, but if we do that, so if I send either 0, 0, 0 or 1, 1, 1, and you receive 0, 1, 1, again, that's not a code word, so something's gone wrong. But if we're assuming at most one digit has been changed, then we can say what the original message was. We can correct the error. So what's happening here is we've got a collection of words. We call it a code, and the words are the code words. So words are these strings of digits or letters. In our case, in this example, the code consists of the words 0, 0, 0 and 1, 1, 1. And then what we do is when we receive a message, if it's not a correct code word, we know something's gone wrong, and we've confined what was the original message, the correct message, by finding the closest code word. So what does that mean, closest? Well, there's this very simple idea of distance between words, which is the number of places where they differ from each other. So, for example, we've received 0, 1, 1. The distance between that and 0, 0, 0 is 2, because they differ in 2 places. Whereas the distance between 0, 1, 1 and 1, 1, 1 is 1, because they only differ in that first position. So we do have a closest word, and then that can be our answer. We think it's the original word was 1, 1, 1, right? So that's how we correct the error. The reason that works is because those code words that we've got are distanced 3 apart. They differ from each other in 3 places. So you can't be distance 1 from both of them. If you're distance 1 from this guy, you must be at least distance 2 from that guy, because they're 3 apart in total. So we can guarantee to be able to correct an error if our code that we've got has this property that all of the words in it are at least 3 apart from each other. They differ in at least 3 places. Okay, so remembering that, what we'd like to be able to correct an error, but have as many messages as possible, as big a code as we can, because that gives the greatest versatility to our system. So how big can this be? Well, let's have a think about this. Maybe we can make it bigger by allowing more letters, right? So we had zeros and ones. So our alphabet was rather small. Our alphabet just had 2 letters. I mean, the English alphabet has 26 letters. Maybe we can use that. And we had words which only had 3 letters in. Maybe we can have slightly longer. So let's imagine that we've got code, and it has got words in it that have 4 letters, and those letters can be drawn from an alphabet. And let's say the alphabet has Q letters. So we had 2 letters, zeros and ones, but we could have more letters. Maybe that gives us more words to play with. So what's the best we could hope for if we want all of those words that are in our code to be differ in at least 3 places? Well, if you've got 2 words in the code, A, B, C, D, and E, F, G, H, if A and B are the same 2 letters as E and F, that's bad, because then it would mean that those 2 words could only possibly differ in 2 places, the last 2 places. So that can't happen. So any 2 code words have got to have, the first 2 letters can't match. So everyone has to have a different first 2 letters. How many different first 2 letters are there? Well, if your first 2 letters are A and B, there are Q choices for A, it comes from an alphabet of Q letters, and Q choices for B. So there are Q squared possible first 2 letters. And so that means the size of your code, you can't have more than that, because any two code words have a different beginning. So that's the absolute upper maximum that you can hope to achieve, right? That's good, if we can get there. Now, here's Latin squares coming back. This is possible precisely when there is a pair of orthogonal Latin squares of order q, so squares of side q. That's super cool. What are Latin squares doing there? That seems really weird. I'll show you. I'll just do a little example. So that's the same theorem I've written up at the top. I'm going to give you just an example here. Here, I've got q equals 3. So I'm making order 3 Latin squares. Those two are orthogonal to each other. And here's how we make the code. For each row and column, we get a code word. So in the second row, first column, this is the code word we're going to make, 2, 1, 2, 3. How do we get the last two bits? So 2 for the second row, 1 for the first column. And then what's the entry in the left-hand square? It's 2. What's the entry in the right-hand square? It's 3. So we can do that, and we can make 9 words in that way. And it turns out this is one of these codes. And the reason is that any one of these words can be completely determined just by knowing any 2 of its letters. That means no 2 of the words can have the same 2 letters in the same places. For example, if you are given the last 2 letters, one of these words, what does that tell you? That tells you the entries in these squares, right? But these are orthogonal, so every pair appears exactly once in that structure. And so we can say exactly which row and column it appears in by just finding it. So that's one, you can check the other possibilities. So this code, and all others you can produce like it, do indeed differ, all the words differ in at least 3 letters, so they can correct 1 error. So we can get this from these Latin squares. It's fantastic. There is a more general result. I will put it there for 10 seconds. You can actually do this. If you have more mutually orthogonal squares, you can correct more errors. So that's really, really cool. Okay, well, let's get back to Sudoku in the last 5 minutes. So we've seen some Latin squares. Not all of those vast number of Latin squares of order 9, of course, are going to be Sudoku, because we have an extra requirement for Sudoku. We need this block rule. So actually, it is known how many Sudoku grids there are. I want to show you a really clever way of finding an estimate of that number that I think is kind of nice and intuitive, and somehow it gives me more information in a way than the exact number does. So I want to just show you what this idea is. So Sudoku have to have 3 properties. They have to be Latin squares, so the numbers appear once in each row and column, but they also are what I'm going to call block grids, that the numbers appear exactly once in each block. So what we're going to try and do is first to establish how many block grids there are. So then they're not yet required to be Latin squares. How many of these grids are there that satisfy this block rule? So we'll do a mini Sudoku example first. So in this size of Sudoku grid, you have the numbers 1 to 4, and we're just interested so far in making the ones that satisfy the block requirement. So in other words, in each of these little blocks, you've got to have the numbers 1, 2, 3, and 4 somewhere, in some order. So how many ways are there to do it? Well, let's just focus on this top left-hand block, and we've got to put the number 1 somewhere. There's 4 places we could put it. And then there's 3 places left where the next number could go. And then 2 places where the next number could go. And then there's only 1 remaining place, and the final number goes in there. So there's 4 choices, times 3, times 2, times 1. We call this number 4 factorial. It's the product, so n factorial is the product of the numbers from 1 up to n. So 4 factorial, that's the exclamation mark, that's pronounced factorial, which of course we can calculate, it's 24. So there's 24 ways to make a block. We've got 4 blocks. Remember, we don't care about the row and column rule yet. So it's 24 times 24 times 24 times 24, which I'm sure you've just worked out in your head is about 331,000 ways to make a block grid. Now, we need more than that. What we next want to work out is actually how many of these block grids satisfy also the row rule, that the numbers 1 to 4 appear exactly once in each row. So let's think about that. Let's think about these top 2 rows. Once you've filled in the left-hand block, which of course there are 24 ways to do, then there's only 2 ways to complete the top row. It could be 3, 4, or 4, 3. There's only 2 ways to complete the second row. 1, 2, or 2, 1. So 4 ways to complete these first 2 rows. 2 times 2. Once you've chosen your block. So 24 times 4 ways to complete the first 2 rows. And then you can do the second 2 rows in the same way. So if you do that, we don't worry about the detail, but I just want you to see the idea of this argument. You get some number, 9,216 block grids that also satisfy the row rule. Now, what we then do is we say, actually, that is a particular fraction of the total number. It's 1/36 of all of the block grids satisfy this row rule. And you can do the same exact calculation, but just tilted by 90 degrees, and say that by the same reasoning, 1/36 of the block grids satisfy the column rule. What we want to know is what proportion of the grids satisfy both the row rule and the column rule. Those are our Sudoku. Okay, so let's move back up to the standard size. With exactly the same kind of ideas, the number of order 9 block grids, so we don't care about rows and columns yet, but those standard Sudoku will have these 9 blocks. Each block contains the numbers 1 to 9 in some order. The number of those this looks quite harmless, but 9 factorial raised to the power 9 is a very, very large number. We don't need to calculate it, but that's how many order 9 block grids there are. And we can do a calculation, it's a bit more involved, that tells us how many of those block grids satisfy the row rule. And it's 1/n of them. You'll notice I haven't told you what n is. I will put it in the transcript, but it's a very large number, which is known exactly. It's something like 128 trillion. We don't need to write it down explicitly right now, but we can work out this fraction. 1/n of them satisfy the row rule, and so also 1/n of them satisfy the column rule. Now here's the assumption that we're going to make, which is an incorrect assumption, but it's useful. We are going to assume that satisfying the row rule is independent of satisfying the column rule. The reason that's a helpful assumption, even though it's not actually quite correct, it's nearly correct but not quite, is that if you've got 2 independent events, then that you can multiply their probabilities to find out the probability of both of them happening at the same time. For example, if you have a pack of cards, 1/13 of those cards are aces. 1/4 of those cards are hearts. So, because those are independent, we can say that 1/13 times 1/4, which is 1/52nd of the cards are aces of hearts, that's what we find in a pack of cards. So if satisfying the row rule is independent from satisfying the column rule, then we could say that 1/n of all of the block grids are Sudokus. And if you work out that number, it's about this big number, 6.657 times 10 to the 21. Big number. What's really brilliant is, I said they're not quite independent, but they're really nearly independent. You can work out the exact answer. It requires a lot of fiddly calculation and lots of computer time. And I'm sure you were almost there in your heads, but it's this. But if you look, that's really very, very close to this estimate. It's a really great estimate. I think it's a useful calculation to do. It's only 0.2% out. So that's how many. We did mention one other question. We know we've got all these grids now, but of course, to make puzzles, you need to remove some of the numbers. How many clues is enough to guarantee that you're going to have a unique answer? So this is counterintuitive again. Look at this grid. It has 77 of the numbers filled in. Surely we can complete this, but we can't. On the top row, on the second row, the missing numbers are 1 and 2. And on the 7th row, the missing numbers are also 1 and 2. There is no way to know how they should go. It's either 1, 2 on the top and 2, 1 on the bottom, or the other way around. We do not have enough information to write this down. So unless you're careful, you risk getting into these situations where even if you have lots of numbers, you can't complete the grid. So this is not a trivial problem. You can't just remove 30 of the numbers and think it's all going to be fine. You have to be really careful that you still have a unique solution. And so we talk about minimal grids, which is where you've got some of the entries filled in, and it's got a unique solution. But if you remove any one of those entries, then what you have then has multiple solutions. So those minimal grids are kind of the best case scenario in terms of you can complete this with a unique solution, but Anything less does not give you uniqueness. And then, if you want to make an easier puzzle, you can add a few things. You know you've got a unique solution by that time, but you can't remove anything. Now, how many do you need, do you think? Well, it turns out there's a lot of activity on this. It took about 20 years to resolve, I guess. About 10 years ago, it was found you have to have 17 entries at least. Not any 17. There are lots of ways to put 17 numbers in that don't give you a unique solution, but 17 is enough as long as you choose them carefully. If you have 16, it's never enough. 16 is not going to be enough. Wherever you put them, however cleverly you place them, you will not get a unique solution with 16. But with 17, yes. But what's not known, and if you're going to become mathematicians, this is still an open problem, how many of these minimal grids are there? What are these minimal grids? And this is an ongoing area of active investigation. And so just to finish, I'm going to mention in 1 minute some variations of Sudoku, like we saw with magic squares. Many variations for you to explore. Bigger doku. Go as big as you like. Cube doku, or hypercube doku. Go as high dimensional as you like. I like this one, Venn doku. These are all Sudoku grids. I haven't put any numbers in, you'll notice. But you could imagine a puzzle where you had 3 Sudoku grids satisfying the Sudoku rules, but there's an overlap, so that gives you more information about the places that are in 2 or 3 of these grids. That means you could get away with fewer clues at the beginning. So that's kind of an interesting question. How few clues do you need? Magic doku, it's also a magic square. Got the Loshu magic square in the middle as well, just for an added little thing. And this last one, now, I don't know if I've invented it. Well, I have invented it, but I don't know if anyone else has invented it. I was trying to think what's like that anti-magic square. So here I present the Sudoku. The rule here is every rule has to break exactly once. So every row, column, and block must contain exactly 3 of the numbers, but not all 4. So the top row, it's got 1, 2, 3. It hasn't got a 4. So this missing square, this empty square, what could go in that square in order to maintain this rule? Well, in that block that it's in, you've got 1, 2, and 3. You haven't got 4. So if you put 4 in there, you'd have a correct block, not allowed. So it can't be 4. Look at the row it's in. You can't put 1 in there, otherwise that row would be right. And the column, you can't put 3 in there, otherwise that column would be right. So for a genuine Sudoku, the only number that can go in that missing space is 2. Now, I have not tried to make an order 9 Sudoku. If you've got a free hour, I invite you to do that. I don't even know if it's possible. But there we are. So that's plenty from me. We'll come back next time. I'm going to be talking about mathematical puzzles and paradoxes, including the one that I've hinted at there. But we'll stop there for today. Thank you very much.
Sarah, thank you very much. And just at the beginning, before we were starting, we were talking about the puzzles in the paper. And Sarah was saying, well, I work so much on this that I actually do the crossword. And I was thinking, well, maybe after this, I'll have a go at the Sudoku. But after this, I think I'll be sticking to the word search, frankly. That was brilliant. Thank you so much. I'm sure you guys have some questions. I'm going to start you off just with a little one from here. So Life a User's Manual. This is an interesting idea. So taking that idea, are there ways that you can actually, this is incredible, the amount of mathematics that goes into preparing the game, let alone doing the game, but are there sort of applications that you can use practically for this sort of logic? And are there any sort of careers that could come out of it?
So, yes, being able to be logical is a good skill to have. So we talked about there are some applications directly of these Latin squares and other kinds of structures like this, but the process of thinking things through and being able to reason our way through a problem, that is a really great skill to have. It can, any job, that's a useful skill to have. But, for example, of course you can become a mathematician, but you could, computer programmers, this is exactly what you do. You have to cover if you're writing a program, you have to cover every eventuality, you have to make sure you haven't missed out any possibility, you've got to follow your way through a kind of branching narrative of the algorithm and make sure that it does what you want it to do. So this is, for me, I mean, writing a program is very like constructing a mathematical proof. And these same kinds of ideas of how is this fitting together, I have to know how it all works, are just absolutely relevant there. So, yeah.
When you were talking about Greco-Latin squares,
Yeah.
you mentioned the 4n plus 2, the
Yes.
6, 10, 14 sequence, and that the 10 one had been solved.
Yes.
I think Ronald Fisher proved that the 6 one couldn't be.
Yes.
Has any progress been made on 14, 18, 22,
Yes.
etc.?
So in fact, it's kind of the worst possible outcome for Euler because, so n equals 2 can't be done, n equals 6, so actually it was a guy called Gaston Tarry who proved that right at the beginning of the 20th century. He proved it was impossible, and it was aptly named a proof by exhaustion because he had to check not absolutely every possibility, but he managed to reduce it. He said everything that we could try is equivalent to one of this still very, very long list of things to check. And he did do that checking by hand in like 1905. Yes, 1959, the order 10 ones were found, and that kind of opened the floodgates because then suddenly there was this, maybe. People had sort of assumed there weren't going to be these others. But actually, it's been shown since then that you can do it for every single order. So 14, 18, all of those, they exist, these orthogonal Latin squares. The only two numbers where it fails are the ones that Euler had direct experience of, 2 and 6. And so, unfortunately, yes, his data set was not big enough to see that the pattern did not continue. So you can make order n orthogonal Latin squares for every n except for 2 and 6.
If you set your terms and you set your constraints, is it theoretically possible to solve any puzzle in the world?
Okay, well, theoretically, but the puzzle has to be set up in order to be able to be solved. So this is one of the things about Sudoku that I say, there has to be a unique solution. So there has to be a solution and only one. So if your puzzle has been designed kind of correctly, then such that that's the case, then yeah, theoretically it can be solved. But it's, of course, actually doing it, as we all know. Sometimes those killer Sudoku, you may not necessarily do it in the most elegant way, but it is theoretically possible to do it, yes.
There we go. Okay, thank you so much. Please join me in thanking Professor Sarah Hart.